Hi, my name is Manish Gupta, and in this video, I'm going to talk about this interesting work called as UITARS, which is about building automated GUI interaction agents using LLMs. Okay, so let's get started. What is UITARS? Well, UITARS is a GUI LLM-based agent that takes screenshots as input and performs human-like interactions. For example, keyboard and mouse kind of operations. If some of you might be able to relate it with Selenium. So, like you can code up Selenium, code up various human-like interactions in Selenium. This is like an LLM-based agent. And in fact, in that sense, it has its own agency in the sense that unlike Selenium, you don't really need to code up things here. It can automatically figure out a whole bunch of things, as we will see in this video. Now, UI agents typically need to have four kinds of abilities. One is perception. They should be able to have real-time environmental understanding. So they should be able to perceive what's going on. And then based on that, take action. So essentially collect the observations from the world, take appropriate actions. So which basically means that they also, in this particular case, it means that you need precise grounding. So the actions here could be like click and so on. So when you want to click, where do you want to click exactly which particular coordinate on the entire screen in the user interface, right? Reasoning. So, these agents should be able to reason. Given this observation and given, this is the final goal that I want to achieve, what should I be doing next? What action should I do next, right? Memory. So these models should also have long-term and short-term memory. So, to store task-specific information. So if these agents are given a task, for example, install something on my laptop, or install the closest printer on my laptop, for example, they should be able to store this task-specific information somewhere. They could also learn from prior experiences. So in their parametric memory, they should be able to encode those prior experiences and any other background knowledge that is required, right? So building these LLM-based GUI agents is not simple. Essentially, unlike regular images, screenshot images are not very, very commonly available. So, there's no good, well, there are data sets, but they're not as large data sets as for usual cats and dogs kind of images, right? And there is a lot of information density on screenshot images. So there are hundreds of elements arranged in complex layouts. And then, an UI user interface agent is supposed to basically accurately still figure out, what is the location of each of those UI components and take the appropriate action on them, right? Um, to take care of these complexity and the requirements, UITARS basically brings in a whole bunch of innovations, as we will see in detail in this video. It has enhanced perception, so it can perceive the world nicely. It has its own action space defined. It's a unified action modeling or action space, which is unified across different platforms for precise grounding. Grounding meaning, rightly figuring out, where a particular user interface, user UI component exists on the screen. So that's that. It can do system to reasoning. So it can do several things, like it can decompose tasks. It can do reflection thinking, understanding what went wrong, why it went wrong. Milestone recognition. It can break down tasks into milestones and figure out a particular milestone has been reached or not, and so on. Right? It can also iteratively train with reflective online traces. So basically, it can try to self-improve as it sees more and more data. Right? So UITARS is basically trained on Qwen2 models, Qwen2 VL models, two different variants, 7 billion and 72 billion, and therefore UITARS model is also available in those two sizes, 7 billion and 72 billion. Trained on 50 billion, trained on pre-training data worth 50 billion tokens. Okay. The most important part, why UITARS is important? Well, it is the state-of-the-art model across 10 plus graphical user interface agent benchmarks across mobile, desktop, and web environments. And that is why it's super important. Okay. So what can you use UITARS for, right? So you can use it for doing tasks of this kind. So look at this task, make the background color of slide 2, same as the color of title from slide 1. Okay. So here are 4 steps in which UITARS is able to accomplish this task. So to change the background color, it has to match the title color of slide 1. So I first need to select slide 2 from the sidebar, right? And this will allow me to access its properties and make the adjustments and so on. So basically, the current snapshot and this is the task. So it clicks there. Then it basically, changes the background to match that. So basically, it clicks into the properties so as to basically be able to figure out what is so the properties box opens up automatically. It clicks onto this background color thing so that it can actually choose from there and then change the color and so on. Okay. What can you, this is another application. So please help me install the Autodoc string extension VS Code in sidebar. It basically starts with an empty screen, and essentially, you can click on any of these apps. So it figures out where is the VS Code app, clicks there, basically tries to figure out the preferences from where it can look at extensions, and then type in Autodoc strings to basically figure out the right extension, and then finally click on essentially install button. Okay. So all of these UX tasks are super difficult, right? I mean, if you really think about it, humans essentially do them step by step, one by one, and we try to figure out on new softwares, we have to basically spend time figuring out how the software works and then do these, right? UITAR just makes it super simple. Imagine yourself, trying to use the Windows troubleshooter. If you've used that, you would basically, you might have really found it very handy, especially when you're in a difficult problem and troubleshooter was able to solve your problem. But several users don't even know that there's a troubleshooter, right? What if those users could basically just talk to their machine and then, just say, hey, Windows, can you install the nearest printer on my laptop? Now, that's awesome, right? I mean, if it can automatically do these steps, it can take snapshots of your screen, do the right click, automatically figure out where to click on the Windows button, open settings, click there, add printer, click, automatically do these clicks, right? Here is another example. I want to show bookmarks bar by default in Chrome. So how do you do that? So essentially, obviously, you start by opening up Chrome and then going to settings, and then in the appearance, change the setting to show bookmarks bar automatically. Right? Now, while these were simple examples, there could be complicated examples, especially those accessing the web and so on. So here, the model is supposed to help users find flights. Okay. Find round trip flight from Seattle to New York City on 5th next month and filtered by price in ascending order. Now that's interesting task. Okay. So here I will also talk about how the model is able to decompose is able to, not just decompose the task, but actually follow various interesting paradigms that we as humans follow when we are actually interacting with user interfaces, right? Task decomposition. So first it sort of understands that, hey, round trip flights, basically it has to break it down into source city, destination city, and then filter by price and so on. Okay. So essentially here it's basically trying to figure out the from city and then enter the city, and then basically it understands, oh, so my source city and destination city is done. There are several steps which I've skipped here. And then, I've been able to reach one milestone. So it has been able to detect that it has been able to do this first milestone, set the source and destination. Next milestone is to basically think about time, right? Essentially, the user said, well, on 5th next month. So essentially, it has to figure out from the calendar. It basically puts up the 5th month there, but it is confused. It doesn't know round trip. What does it mean? So it can, here it basically clicks on search, but search gives you an error. So it basically gets into reflection mode. It is able to sort of think why this error could have happened, and therefore starts basically filling up the return round trip, right? So essentially the return date as well. Once that is done, complete date selection milestone has been achieved. But still, it is not able to actually click on the sort button because it has to sort by prices, right? So it is not able to sort, and therefore it basically waits for some more time until the page loads, and then it figures out, oh, page has loaded fully now, and I can actually click on the sort button. It basically clicks on that sort button, and then finally, essentially, is able to sort by price in the ascending order, and then complete the final task. So you see, I mean, here the agent is able to do several things. It's able to decompose the task, understand that it has completed some milestones, also do trial and error kind of understanding, reflection, and so on. It is able to do a whole bunch of things. So what are the capabilities that a user interface agent should have? Well, as I mentioned slightly earlier as well, it should be able to perceive the environment. It should be able to perceive structured data in the environment, textual data in the environment, even screenshot data from the environment. Okay. It needs to have short-term memory and long-term memory. Short-term memory could basically be passed as part of the prompt itself, the context in the prompt itself. So what is the, I mean, at any point of time, these agents, basically these embodied agents, so to say, when they actually do hardware controls as well, they typically need to have three things at every time step. One, observe the environment, so observations. Second, thinking. What is the current thinking that I have based on the observations? And third, action. Okay. So to be able to do this, they can use their short-term memory. So they can keep an action history, what all actions they have done in the previous time steps, and what were the observations, what were the thoughts, and so on. And then they can also have long-term memory in their pre-trained weights themselves, or their fine-tuned weights in that sense, right? So which can store previous interactions, background knowledge, prior tasks, and so on. We need to have the reasoning abilities, both system one fast thinking ability and system two slow thinking abilities, as I showed to you in the example, task decomposition, long-term consistency, ensure that you're following the same kind of patterns and themes to be able to do the task. Milestone recognition, understanding that certain milestones of the entire big task are done, right? Trial and error reflection, as we basically saw in the previous task, right? They should have a definition of action space, what all actions they can do. They can click, they can scroll, they can type, wait, what all actions can be done. Plus, they should be able to also ground those actions. So if you have to click, where to click exactly, right? Or if you have to scroll, how much to scroll, and so on. Finally, there should be an evaluation framework. One should be able to evaluate the ability to perceive, the ability to do grounding, or other figuring out where the exact user interface element is to be clicked, and so on. Also, ability to do offline agent capability evaluation in the sense that the agents can be used to do two kinds of tasks, offline or online user interface tasks. Yeah. So offline tasks are tasks where the agents just perceive the environment and then make some final insights out of it. But online tasks are where they actually interact with the environment and make changes in the environment, and then they make more observations and so on. Right? So here again, the evaluation could be in terms of task completion. So were they able to finish milestones? Were they able to finish the full task, and so on? Okay. So these are the capabilities that are required in a user in a UI agent. Now, to think about it, UITARS has been trained using the Quen 2 VL model, but it has also been trained using user interface related data. As I mentioned earlier, this data is very scarce. So therefore, these guys basically made use of all possible openly available data, plus they actually gathered a whole bunch of their own data. Now, the data set in their case looks very interesting. And this is a slide which basically tells it all. Okay. At the center, you basically see Outlook, which is opened. So essentially, there are some emails, and the second email is actually, there's a right click which is done so as to open this pop-up menu. Okay. So what is the kind of data that they actually gather based on such screenshots? And remember, these data, which I'll talk about, are gathered using GPT-4V and much larger models using prompt engineering. So these models are actually given the image, and they are basically given a prompt so as to gather the kinds of data which I'm going to talk about. Okay. The first information is going to be task grounding. So in the sense that you could basically just ask based on the screenshot, hey, help me delete this email. And then what is the answer? Well, the answer is basically the coordinates of this rectangle, because the delete rectangle, right? Delete button. So this is the answer. And again, how is the answer being obtained? By actually prompting based on this question to GPT-4V and such larger models as to get the right answer, and use this data to actually train your Quen 2 VL model. Hey, this is the query. Tell me what should be the answer. I mean, which is the box coordinates where I should click to be able to delete this email, right? Second one is element description. So basically, given this element highlighted by the rectangle, just describe this element, right? And descriptions are of 4 different kinds. Visual description. So it's a button with the text new email and an envelope shaped icon above it, right? Positional information. So it's located on the upper left corner of the page. And it's basically the first button on the home tab, very detailed description generated by obviously the large visual language models. Okay. Element function, so what is this useful for? So this button is interactive, clicking it will take you to the new email button and so on. Element type, so is it basically button? Is it like a list or a checklist or radio button and so on and so forth, right? I mean, you have so many interesting UI elements, okay? Question answering data. So essentially, I can actually ask a very interesting question on this image. What is that app with the waveform like icon, okay? And now, obviously, there is no, I mean, model has to first figure out where is the waveform like icon. And well, the waveform like icon is right at the bottom right there. And then it basically comes up with this nice, it should be able to come up with this nice answer that it's the Windows Task Manager and it's used to do blah, 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 and so on. Okay. Set of mark perception. So the idea here is that in this particular task, the model is actually given this image and this green oval marked on it. And then it is basically asked, what is the text inside the green circle section? And then, the model is supposed to be able to answer that. Or it can be, given this marked orange rectangle, and the question is going to be, what are the elements inside the yellow bounding box? Sorry, it's yellow, but anyway, right? What are the elements inside the yellow bounding box? So the model is supposed to answer it's a button containing the text, poster, reply, and so on. Okay. The model is also asked, or rather, another kind of data which is gathered is dense captioning data. So given this image, just tell me what's there in the image. What can you understand from the image? Okay. So all of these data are collected over hundreds and thousands of such snapshot images across several apps, both online. Typical apps on desktops, on mobiles, and so on. Right? Various websites as well, various web portals and interactions with them as well. Okay. So that's that. Now, so far, I've not talked about, I've talked about static snapshots, but what if I want to know what happens when I click somewhere, when I do an action and a transition happens to another snapshot, right? How do I learn about these state transitions? And that is why I did the state transitioning captioning as well, where basically the model is given two snapshots, and then it's asked very interesting questions about, what led to this second snapshot, what changed, and so on and so forth, right? So all of those data are actually used to further pre-train this UITARS model on top of the twin 2VL pre-training. Okay. Now, the pre-training tasks basically are very related to the data that you saw on the previous slide. You enumerate all visible elements. So these are the tasks on which it is basically pre-trained for. Enumerate all visible elements within a screenshot, generate their element descriptions, conditioned on the screenshot. Remember, all of these are very user interface based tasks, right? Caption the entire interface while maintaining accuracy, minimizing hallucinations. This is dense captioning, basically. Identify and describe the differences between two consecutive screenshots. This is basically, state transitions, so state transition captioning. Also determine whether an action such as mouse click or keyboard input has occurred, right? Question answering, set of mark prompting, we already discussed those. Also predicting the coordinates of the elements it needs to interact with. For example, where is the red button in the top right corner labeled submit, right? What they also did was to manually design this nice action model, which basically unifies across various apps, and for mobile phones, there's a separate one, desktops is a separate one, and shared between desktop and mobile phones right here. So obviously click and drag are shared, but then tap is basically very mobile specific and so on. Okay. So all of those, like the tab and the tap, are basically or the click and the tap are basically, combined together so as to basically call a shared click action in that sense. But then on mobile phones, you have like press back and press home, press enter, and so on. On desktops, you have hotkeys and so on and so forth. Okay. Now, the way the model is trained is basically, it is given a task instruction. As I showed to you, there were several tasks, right? Like book of like and so on, task instruction. And then the model basically, based on the task instruction, and an observation. So it is also able to observe the screen, right? It is basically given the screenshots. So the model is basically told that, hey, here is the task instruction, here is the screenshot. Now, which is basically the observation. Think what is the next step that you should do, and then based on that, do an action. So basically, the thought and the action needs to be generated at any time point by the model. Now, obviously, the model can actually make use of the historical tasks up to n levels of history and different time steps in the history. To be able to, and the current observation to be able to decide what should be the thought at this time point and the action to be taken. To be able to train the model better, obviously all of this data was used, which I talked about so far, but they also infused system to reasoning. So what does that mean? They basically crawled a whole bunch of GUI tutorials. So there are these graphical user interface tutorials, millions of them. They basically gathered them and essentially further trained the model using that kind of data. The other way in which they do system to, and these tutorials basically talk about all of these user interface controls and how you can manipulate them and so on and so forth, right? So very important data, okay, for a UI agent, obviously, right? The other thing that they did was to basically do reasoning stimulation with thought augmentation. And let me talk about this, okay? So imagine that you want to train this model to be able to do the right next few steps so as to achieve the final goal, right? How can you train it to do so? So you basically give it a whole bunch of instructions. So as you can see here, you basically give it a whole bunch of instructions to be able to sort of, do some task. You give an instruction for a task, right? The model actually comes up with several steps. So basically there's an observation, there's a thought, there's an action, and that repeats for several time points. Okay. So what you do after a few time points, after your certain history, is to basically make sure that that you train the model to be able to predict the thought, given the current action. Okay. So the idea is that you are asking the model to be able to predict the thought given the action. Typically, what happens is that the thought happens and then the action happens, right? But one way of making the model come up with more awesome thoughts is to give it the ground truth action. Tell it, hey, this is the action that you should be doing. And based on that, can you come up with interesting thoughts? And then obviously the data, the ground truth data for this is generated using the large visual language models. And those large visual language models have been told that, hey, this is the task. This is basically the history, observations, action, and thought history. And this is the action that I'm planning to do on the current observation. What should be the thought that the model should think so as to be able to do this action? Okay? And while doing so, it is basically motivated to come up with the thoughts which can lead to task decomposition, long-term consistency, all of those goals, right? Milestone decomposition and so on. Okay? That's one way of basically infusing system-to-level reasoning into the model. Another way is to basically, have the model do the task, come up with several thoughts and actions at any time point. Given a time point, there is a history of thoughts and actions which has happened, right? Current time point, you have the observation, you have the history of thoughts, actions, observations, all of that. And the model is basically told to sample many thoughts, thought action pairs, thought action TA pairs, thought action pairs, right? And then what you do is to choose that thought that led to the right action. Okay? Now, obviously, if you sample many thought action pairs, not all of them correspond to the ground truth action. So therefore, what you do is to basically sample many of them from the current model, and then you basically tell it, okay, you did wrong here, but this one is the correct one. And therefore, I'm going to use it to further pre-train this model. And therefore, this is the way I can infuse system to reasoning into it. So that's how they basically do further training, to be able to infuse system to reasoning it. Now, yet another thing that you could do is to learn from prior experience in long-term memory. So the way they do this is as follows. They basically have the current version of the model. They have a whole bunch of task instructions, a book of light and so on, right? They ask the model, hey, can you basically generate the entire trace? Trace basically meaning, observations, thoughts, and actions. So basically the model comes up with all of those things, observation, tasks, and actions, a sequence of all of them, okay? And then they pass it through a filter. Now, obviously, the model can make mistakes here, right? So therefore, they pass it through 3 different kinds of filters, rule-based filters. The model might just be blatantly doing something wrong, right? It's basically telling, hey, click on this radio button. Well, there's no radio button on the screen. How can I click? So rule-based, you can basically just delete some of those traces, filter out those traces. Okay. You can also filter out traces using humans. People can actually sit down and label some of those traces and say they are wrong, right? You can also filter out those traces based on a visual language model, large one, right? So basically, you take a whole bunch of traces which are generated by the model to do a task. You filter the bad ones, and then you have very high quality data. And you use this high quality data to be able to self-improve, to be able to further train the model to self-improve. You could also basically, by the way, pass it through humans and actually, have humans generate more tasks or also, clean them up further and so on. So they basically also have this self-improvement loop. Even without humans, it can actually, just the rule-based and the visual language model-based feedback is actually very important for it to filter from this from these set of traces that it generates. They run it on hundreds of machines, instance of this model, and then keep improving the model in that form. Okay. Now, yet another way of improving the model is to do something called as reflection tuning. And the way this is done is as follows. And this is obviously done with human in the loop. So basically, what the model is basically asked, take the instruction and come up with this trace, basically observation, thought and action kind of triplets at different time points. Okay. A human actually looks at the trace and figures out that the model has made an error at this time point. Right at this rth time point, the model basically just made an error in the thought that it came up with, and therefore the action was also wrong. So this is where the human can come into picture and come up with the right thought and the right action. Okay, so thereby giving you an example of the preferred sample and the not preferred sample, saying that this is a wrong sample, this is a right sample. The right sample is obviously labeled by the human, so you know that is right. So this is called as the error correction trace pair. And when I talk about preference samples, one positive, one negative, I think it should basically clearly tell you that people do DPO. These guys do DPO with it, direct preference optimization, so as to be able to make the model even better. Okay? Yet another way of coming up with preference data is basically a post-reflection trace pair. The idea is that you let the model again take the instruction, come up with trace, as you can see here. It makes a mistake, and you don't stop the model. You let it make the mistake and go further. Okay, and the model basically takes up, makes a mistake, keeps moving on even after making mistake, right? And then basically it comes up with the next thought at r+1 timestamp, and then the action corresponding to it. This is where the human intervenes. The human basically says that, hey, yeah, the model has made a mistake. Let me help it recover from that mistake. So this is the way of actually telling the model how you can actually recover, how you can do reflection on the mistakes that you made and still recover and get to a good state, right? So basically, therefore, this green one, the R+1 timestamp is what the human labels. And then the DPO is basically done by considering everything up to the R timestamp as the context. And the preferred sample is obviously the green one, and the not preferred sample is the black one, where an error was made by the model. Okay? So this is how reflection tuning is basically also used to improve the model. Now, what is the result of all this? As I mentioned at the beginning of the video, UITARS is a really awesome model for UI-based tasks. Across various benchmarks, in fact, like 11 different UI-based benchmarks, the model has been shown to outperform GPT-4o and Claude significantly. So as you can see, this is the interesting plot, 11 different tasks. You can see for each of the axes corresponds to different tasks. And what you can observe is that GPT-4o, the green one, is actually very, very small area, right? Essentially saying that it is actually much worse compared to the UITARs. Okay. As you can see, the UITARs, 7 billion, 72 billion, 72 billion can actually lead to very high improvements on some of those models, some of those tasks, some of those benchmark tasks, right? So in short, it achieves state-of-the-art performance in 10 plus GUI agent benchmarks, which basically evaluate different perspectives of user interface understanding, like perception, grounding, and task execution, right? So in summary, in this video, I talked about UITARS. UITARS is a GUI agent, a GUI agent that integrates perception, action, reasoning, and memory into a scalable and adaptive framework. It has been shown to outperform Claude and GPT-4o on 10 plus GUI benchmarks. And the training involves significant innovations. First innovation was in just getting this interesting data set, right? I mean, screenshot images are not very common and they're very complex, high density, high precision required, right? But there were so many interesting innovations as well, like enhanced perception, rather than depending on HTML tags. Now there is perception in terms of images, and very, very accurate grounding. So being able to say that, hey, this is where the user interface element exists on the entire screen, right? They also did unified action modeling so as to not have too many different action classes and be able to work across different platforms, generalize across platforms. They also perform system to reasoning by doing all of those interesting things. Making the model iteratively refine and also train it on GUI tutorials data and so on, right? And then they also have iterative refinement using online traces, direct preference optimization to further improve the model. Okay, so that's it for this video. Hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.